So you can see the slides over there.
Yeah.
And could you also please relay the questions, audience questions, so that the online audience can get it. Yeah, thanks.
You want to put that in your pocket?
Slides.
Yeah.
Put that one in your pocket, maybe. That the mic thing.
The mic.
Okay.
I think that one is working.
Okay. Yeah, okay.
Can get started?
Okay, let me just. Can you try again?
Hello.
No, yeah, clicker.
Hello everyone, I am Sanyam Agarwal, a PhD. Yeah, sorry. Yeah. Okay. I am Sanyam Agarwal, a PhD student at Saarland University, and I'm going to talk about Nullstellensatz for approximate polynomial satisfiability. This is based on joint work with Shagnik Datta, Anurag Pandey, and Himanshu Shukla. So before I begin, I would like to thank the organizers for inviting me for the talk and for the wonderful workshop. I'll also like to thank them for scheduling Robert's talk before me, because a lot of what I'll talk about he has already covered, so makes my job easier. And so let's begin. Yeah, so as we know, exact polynomial satisfiability, suppose we have two polynomials f and g, where g is xy equal to 1, the hyperbola, and f is the straight line x equal to 1. Then we know that this has one common root at 1, 1, right? And another another formulation for this is if we consider this as a polynomial map where basically the polynomial map phi sends each input coordinates, like the input vector, to the evaluations of the input polynomials. And now we want to look whether 0 lies in the image of this. Like this is equivalent to checking if this has a common solution, right? So, but sometimes exact polynomial satisfiability can be a very strong ask. So, like similarly, we can define approximate polynomial satisfiability. Here we have polynomials x equal to 0 and xy equal to 1. And now you can see that geometrically these two curves never meet, so there is no exact solution. However, if you go near and near to the y-axis, then you see that they sort of converge, right? So this is a notion that we can capture if we allow these input variables to take values in epsilon, in some field C epsilon, where epsilon is an arbitrary small parameter. For instance, in this case, if we set x to epsilon, y to 1 by epsilon, then both f and g are order epsilon polynomials, and hence they are 0 mod epsilon. So this problem was introduced first by Go, Saxena, and Sinhababu in a paper in 2018, and they showed that they had efficient algorithms for this problem, and they showed that this could be used to construct efficient hitting sets for VP bar. And another way, they also showed that similar to the exact case, this also has an alternate formulation where you now look for whether origin lies in the closure of the image instead of simply the image. Okay, and now we can generalize to more than two polynomials. For instance, if we have, okay, so first thing is, in this talk I'll restrict to polynomials over complex numbers. And yeah, so suppose we now have m polynomials over the complex number over n variables. Then you know that then we can define the vanishing set of this system of polynomials as all the common roots of these polynomials. And analogously, we can define something called the approximate vanishing set, where we now allow the values to actually be the variables to actually take values in this function field, and the only restriction is that the constraint is that all the fi should now be 0 mod epsilon. Okay, and formally the question of approximate polynomial satisfiability, it asks whether the approximative variety of this system of polynomials is non-empty. And this, as I talked about, this captures this captures border phenomena in GCT. Okay, any questions till now? Okay, so now so in this work we start with this notion of polynomial satisfiability. Before that, we need something called the annihilator, which is for a given system of polynomials, Annihilator is a polynomial that when we, over a different ring, for instance, where if you set each variable as the one among the input polynomials, then it evaluates to 0. And so the main result that Guo, Saxena and Sinhababu showed was that actually this approximative variety is empty if there exists even one annihilator of the system of polynomials which has a non-zero constant, right? And the starting point of basically our work was the observation that this is like very, very similar to what we see in the classical case. So in the classical case, we have that the variety of this system of polynomials is empty if as Robert talked about, if summation fi gi is 1, or like one lies in this ideal, right? And you can see that in the approximative analog, we have that this approximative variety is empty if there exists some annihilator with constant term 1. Okay. So naturally, our first thought was to whether this system also has some analog of the strong Nullstellensatz. In the classical setting, the strong Hilbert Nullstellensatz answers questions about containment of vanishing sets. For example, we have this criteria that if Vf1 to Fm is contained in Vg, then G lies in the radical of F1 to Fm. And so the analogous approximative analog is that is there a algebraic criteria such that we can characterize whenever G contains the approximative vanishing set of Fi's. Okay, and so our main result is the following, that in fact there does exist a criteria, and that if the approximative vanishing set of G contains the approximative vanishing sets of Fi's, then actually there exists some natural number where you can write, essentially you have a polynomial in G which has coefficients of this form, which are basically rational functions of this form. And so what was interesting to us is this is not just some algebraic abstraction, but essentially this relates very well to some well-studied notions in commutative algebra. For example, if you now restrict yourself to the ring, which is basically the algebra generated by Fi's over complex numbers, and then you take the maximal ideal of that ring, which is essentially only the ideal of these polynomials, and then you look at the localization of this ring, then essentially this gives that the approximative vanishing set containment holds whenever this G is integral over this maximal ideal over the local ring. And integral is essentially it has a monic polynomial. And yeah, so basically, essentially like strong in the classical setting, it relates to radical questions, and in the approximative settings, we find that this relates to integral closure. Okay. Yeah, and so for instance, this can be a useful criteria in this sense. For so if we have these polynomials, at first it is not obvious whether this approximative vanishing set of G contains the approximative vanishing sets of F1 or F2, F1 and F2. However, we see that the strong approximative Nullstellensatz, it gives a short certificate because we can write G square in this form. Okay, so so now I'm going to talk briefly about the proof techniques that we needed. So in the classical, so I'll first begin. So yeah, in the classical setting, the weak Hilbert Nullstellensatz and the strong Hilbert Nullstellensatz are known to be equivalent, and this happens through this like very beautiful application of something called the Rabinovich trick, which essentially states the following, that if the vanishing set of G contains the vanishing set of some polynomials F1 to Fm, then this is equivalent to checking that the vanishing set of this bigger system F1 to Fm and 1 minus Gy, where y is a new variable, is essentially empty. And we know that the thing on the right hand side is actually just the weak Hilbert Nullstellensatz. So essentially we have converted the strong question into the weak question. And intuitively this works because suppose the left hand side holds, that is, so if Fi's were vanishing and G was also vanishing, there is no way that 1 minus Gy can vanish. And so there can be no common root of this new system. And then you can show that if this is empty, then using the weak Nullstellensatz, you can write one as the summation of these things, and since this holds in the ring, this also holds in this where the xi's are sent to the fraction field, and then you get that g lies in the radical of this ideal of f1 to fm. Another great thing about this was that this also shows that WHN and SHN are computationally equivalent, because whenever you solve whenever you solve WHN, you can always solve SHN. Okay, so naturally we tried to see whether this already generalizes to the approximative setting, and we found that this unfortunately does not hold. And the intuitive reasoning behind this is the following, that here if we even allow f1 to fm to approximately vanish and g to approximately vanish, since y can now be allowed to, since we only need one, since g is only order epsilon, we can set y to the inverse of that thing, and we can get 1 minus yg is still 0. So essentially what we need to prove, what the Rabinowitz trick in this setting would need is the following two things: that when fi's are vanishing, then g should not diverge, because we want g to vanish, and also that it should not converge to any non-zero constant, right? And we show that you can actually capture these two things by the following two criteria. So first I'll talk about the non-divergence thing. So what as I talked about, the issue with just using the classical Rabinowitz trick was that y could essentially diverge and as in become something of the type 1 by epsilon, and then it could become arbitrarily large. So if we include y in the set of input polynomials already, then this fixes y to also be order epsilon. And secondly, we want that g should not be a non-zero constant, so we just add for all non-zero constants, we add that this should not hold, right? Okay. Yeah, and now we show that if you actually apply these two criteria using the weak approximative Nullstellensatz, that is that there exists some annihilator with a non-zero constant term, then you get the following two conditions. So the non-divergence thing already gives us that we get this sort of polynomial relation in G, where the QIs are actually polynomials where the input variables are substituted to these f1 to fm, and with the constraint that the highest degree polynomial QR has no constant. And now when we take this formulation along with the non-zero constant limit condition, then we can show that actually we can get a more refined system such that now each of the FIs are constant free. However, the small thing is here L can still be greater than R, so this does not directly give us the criteria we wanted, because for integrality we need all the right hand side terms to have degree less than R in G. So yeah. Okay, so now you might wonder that here the non-zero constant thing was supposed to hold over all non-zero constants, which are infinitely many. So how can you even start to capture this in a finite way? So the interesting thing we found was that once we get this characterization, we can actually once we get the characterization for the no divergence condition, and we start to interpret this as a polynomial in G, then already you can separate it into sort of two polynomials, one of which is constant free and one which has constants. And then the polynomial which has constants is actually a univariate polynomial, so it has only finitely many roots. So actually we only need the second condition for these finitely many bad points in the over all these non-zero constants. So, and this is how we can actually move to this criteria. And then finally, to prove the criteria, we can do some algebraic manipulations to decrease this degree L to less than R by repeated multiplications. Okay. Yeah. So now I'm going to talk about the computation part. So Guo, Saxena and Sinhababu showed that actually the weak approximative Nullstellensatz or the APS question is actually in PSPACE. And as I talked about, they used it to generate efficient hitting sets for some problems in GCT. And also, like in the classical setting, WHN and SHN are computationally equivalent. But even though like we have an analogous a strong Nullstellensatz in this approximative setting, the procedure is actually not computationally equivalent because we needed many of these equations as I talked about. And so now again, formally the decision problem is that when you have input polynomials given as algebraic circuits, can you decide whether approximative variety of G contains the approximative variety of F1 to Fm? And yeah, we have many Rabinowitch tricks, so we can't directly say that this is equivalent. Yeah, and one thing was, so this approximative criteria, it gives us something like integral closure. And so some related notions have been studied in literature. For instance, one is subalgebra membership, where you want to see whether this polynomial G lies in the subalgebra generated by F1 and F2. And so so this is, so we just say that this is not equivalent to our the integral closure criteria, because for instance in this example the approximative variety of G and F1 are equivalent, but X is like G is definitely not in the subalgebra. The closest notion actually comes from maths a lot. So there has been some work on something called Nullstellensatz, where essentially they are studying something like this. So now they allow these FIs to still take, like these variables to still be from C epsilon, but each of them are allowed to be some finite constant in on the evaluation and not 0. And then they want whether G also takes some constant value. So this is, while very close, it's not exactly the same thing, because we talk about vanishing and they talk about being well behaved in the sense that everything converges to some finite value. Okay. So yeah, and the computationally we can show that SAN is also actually in PSPACE. This is done using essentially, like we essentially prove effective versions of the approximate Rabinowitch tricks that we had, and we do this by using annihilated degree bounds which are known due to Perron and Kayal, and also, so Saxena and Sinhababu had this random reduction trick which essentially says the following, that if you have some k polynomials whose transcendence degree was, let's say, R, then you can always restrict to some R plus 1 random linear combinations of these k polynomials, such that the approximative variety is, non-emptiness of the approximative variety is preserved. And once we apply these two things, we get a exponentially sized linear algebra system, which, as Robert talked about already, can be solved in PSPACE. Essentially, this is how it goes. So you have circuits for F1 to Fm and G. You can so Saxena and Sinhababu also showed that you can compute the transcendence degree of these polynomials in PSPACE. Then you reduce to a rho plus 1 random linear combination. This ensures that the annihilator ideal is now principal, so the minimal annihilator would have singly exponential degree bound, and so essentially all the degree bounds in the all the degree bounds of the polynomials that appeared in our Rabinowitch tricks is now singly exponential, and you can then solve this linear system in PSPACE. Okay, so this is mainly what I wanted to talk about, and so we talked about that one, like APS is actually like the weak approximative Nullstellensatz, and we can prove a strong version which actually relates to integral closure. And even though at first it seems that because of the infinitely many conditions that we need to check, this could be exponential space, we can still get a PSPACE algorithm. So we believe that this actually opens up a lot of interesting questions in this area. So first thing, and we believe the most important thing right now, is to see whether there's actually a useful notion of dimension in this setting, because like geometrically it is important to characterize how big such a vanishing set could be. And also, as Robert talked about, like in the proof of, so if we even want to improve the computational complexity of both these questions, and we want to suppose generalize the ideas that they have, then you need something like, so as you talked about the Poisson formula, which essentially iterates over the finiteness of these roots. However, in this setting, for even the simplest example, for instance, x is equal to 0 and xy equal to 1, all the assignments like epsilon comma 1 by epsilon, epsilon square comma 1 by epsilon square, all of these are roots. So even though these are like finite degree, finitely many polynomials, there are there are infinitely many roots in that sense. So can you like describe a canonical notion of a root, and maybe that is useful to define the dimension also, and also to generalize the techniques of these multivariate resultants to improve the complexity. Okay, so another interesting thing in our opinion, something that I didn't talk about, was that you can actually show that this integral closure is finitely generated as a module over the local ring. So, and also even if you restrict, since the local ring is a Noetherian ring, even if you restrict to this, restrict to only polynomials in the integral closure, that are also finitely generated. However, we have absolutely zero handle on how to algorithmically obtain these generators. So that is another interesting question. And yeah, so something that is not on the slide, even like generalizing something like Grosvenor bases in this setting. So we tried, so there is something called Mora's algorithm that works over local rings. We looked into that, but that doesn't seem to work. So yeah, like all of this in our opinion is very interesting and open. Yeah. Okay, thank you.
And this, in your example of like the x1 minus 1 and then x, right?
Yeah.
And I think if you just take the projectivization of that, you get a solution.
Yeah. So it is different to projective roots because, for instance, you have x equal to x plus y equal to 0 and x plus y equal to 1. There is still a projective root, but there is no approximate root. Yeah.
Yeah, that's what I was simple.
Other questions?
So you mentioned GSS and a few instances. So one of the we talked about this. One of the highlights there is that they can actually solve. You mentioned this transcendental root in AM intersect YM.
Yeah.
I was wondering, like, as you mentioned, I was wondering if you have any implications or any way to use it.
Yeah.
What
So
about the approximate setting?
yeah, we haven't really thought about it, but yeah, it's an interesting direction. Yeah. Yeah, so as I mentioned, like everything is open in this setting right now. Yeah.
That's open questions. Any more questions here? Alright, then let's thank Sanyam again.
Thank you.